All right, let's do this, guys. Let's see. Chapter 8, more than 5. Washing machine purchased for 256. So that's your principal. It's your original amount. Each year, the value is one fourth of its value the previous year. Each year, the value is one fourth of its value the previous year. Okay. All right. So that means that we've lost. Right, so that means you lose 75%. Right. So this is you're decreasing by 75%. Or does that mean that you're decreasing by 25%? Okay, what does that mean? Each year, the value is one fourth of the value the previous year. Right. So, for example, if you have something that's $100, right, and one fourth of that, so you multiply it by 25%, which is going to be 0.25. Okay, what do you get? So 100. You multiply by 0.25, you get $25. So is $25 one fourth of the value the previous year? Yeah. So it's actually going to be this one right here. Okay, so it decreases by 75%, which means that, so let's write this equation properly. So this should be 0.25 instead. So we have 256, and we're going to multiply it by 1, and because we're losing 75, by 1 minus 0.75 to the t power. Right, so, and what should we call this? Right, this is washing machine, so we'll call it WT. Okay, so we'll call it WT. Okay, so if we rewrite this, we'll get 256 by, and 1 minus 0.75 is going to give you 0.25. And this is the t power. Okay, so let's see. Um, let's see, what is this each year? Okay, I think the wording is wrong, but on number 1 here, it says each year the washing machine loses a quarter of the value each year. Okay, and then how much of the value does it keep each year? Okay, so actually let's go along with what it says. So I was trying to do all of it at once, but, and so if you have 100% and it loses one fourth, which is 25%, which is going to be 0.25, how much does it keep each year? I was thinking that it didn't actually make sense. All right, so if you go 100% minus 25%, you get 75%, or you can call it, you know, actually it shouldn't be 100, it should be 1. So 1 represents 100. So if you go 1 minus 0.25, you still get 70.75. And so how much is the value? How much of its value does it keep? It keeps 75%. So we want to call it 75, 0.75, or you can call this 75%. Is the value increasing or decreasing? And this is definitely decreasing. Actually, yeah. And whether graph that models the situation linear or exponential. This is anytime you see something like this where it's not the same every year. Okay, it loses one fourth, but each year it's a fourth of what that year is. It's not losing $4 or or 10, where it's not losing 20. It's actually a fourth of it. So it's actually a exponential. So this is going to be exponential graph. Decreasing means you get an exponential. Okay. Oh, number 3. This is what I wanted. Write a function v of t that describes the value of the washing machine in dollars as a function of time in years t after the initial purchase. So this one's going to be, and this is what I started doing at the beginning. So this is 256, and this is going to be 1 minus, because we're losing, right? And it says that it loses 1/4 of the value. So it loses 0.25. Okay. What it says up here is that the value is 1/4 of the value previous year. Okay, that's actually something different. So these two are not the same thing. Okay, that's not the same thing. So losing 1/4 of the value, and it's worth 1/4 of the value is different. So that's why I was a little confused at the beginning. But I, think we should just go along with what the 1, 2, and 3 say. And this is to the t power. Okay. So you can leave it like this, or you can write it as 256, and the 1 minus 25 is going to be 0.75 to the t power. Okay, number 4. So sales clerk yearly salary is 50,000. Each year she will receive a 2% salary increase. Okay. Is a salary increase or decreasing, right? So this is going to be increasing. And this graph will be exponential. Create a function s of t. So we'll go with s of t. Okay, so we start $50,000. Okay, and then this is going to be 1 plus the rate. The rate is 2%. Right, but 2%. You're going to move the decimal back, which is at the end of the 2. It's going to look like 0.02. So it'll be 1 plus 0.02. And this is the t power. Okay. Again, if you want, you can combine it and do it as 50,000 times it by 1.02 to the t power. Okay. Okay, number 6, this expression show below defines the functional models of future population of red cats in a wildlife reserve for X months. Okay, right here. What's the monthly growth rate for the red cat population as a percent? Right. So if we know where to look, and we've done this before, but this right here is going to be the population where we first started looking. The 1 plus the 1 and some more means that it's a growth, right? And how much is it growing by? It's growing by this much right here. That's how much it's growing by. So let me write that down. It's 0.0117. Okay, and that number 0.0117, that number, that's a decimal. If I turn it back to a percent, that means I can move it 2 places to the right. So my number will be 1.17, and this will be percent. What's the monthly growth rate for the red cat population? Okay, we'll say growth rate is 1.17%. Determine whether a function represents exponential growth or decay. Remember, growth is just bigger than 1, right? So it's just 1 plus. Decay is going to be less than 1, or we call it 1 minus. Yep. So 1/2, you look at this, 1/2 is going to be a decay because it's less than 1. 3/2, 3 divided by 2. If you use a calculator, you don't know. So it's not always a fraction. If you go 3 divided by 2, you get 1.5. So that's a growth because it's bigger than 1. 7/8. How much is that? Right? So you use a calculator. 7 divided by 8. You get 0.875. That's smaller than 1, so that's a decay. 4/3. Okay, 4 divided by 3. Use a calculator if you don't know what that is. But 4/3 is going to be bigger than 1 because it's 1.3. So that's going to be. And this last one's a little weird. It has a 3 in the front, but we don't care about that. We just care about. We're just going to be worried about the base, right? The base is 1/3. So 1 divided by 3 is smaller than 1. So we're going to go ahead and just say that's a decay. All right. All right. That's it.